pen ink inside a rock from Mars. Not from a spacecraft, not from an astronaut. These rocks flew here on their own, across millions of kilometers of space. And scientists still found synthetic pigments, polyester fibers, and microscopic diamond particles locked inside them. The contamination didn't come from Mars, it came from us. But the part nobody talks about is what that contamination actually destroys. In the next few minutes, you'll see why fewer than 400 rocks make this one of the most fragile scientific archives on Earth, and why a single polyester fiber can permanently close a question we only get to ask once. Out of nearly 80,000 meteorites ever found on Earth, fewer than 400 are confirmed to have come from Mars, less than 0.5%. The Natural History Museum in London, one of the world's leading collections, holds just 20 of them. No mission has ever returned samples from Mars. That means every Martian meteorite sitting in a lab or a museum right now is the closest thing humanity has to a physical piece of another planet. There is no resupply, no one can order more. When researchers published findings in Applied Geochemistry identifying synthetic pigments from pen ink, polyester fibers, ethyl alcohol, and microscopic diamond particles inside Martian meteorite samples, the scientific community faced an uncomfortable realization. The way humans handle these rocks is actively degrading what the rocks can tell us. The most famous Martian meteorite in history is catalogued as ALH84001. It was discovered in Antarctica in 1984 and then sat in storage for a full decade before anyone looked closely enough to care. When scientists finally examined it, they found what appeared to be possible signs of ancient microbial life. That claim briefly made global headlines and sparked one of the most heated scientific debates of the late 20th century. Most of the evidence put forward at the time has since been challenged or discarded. But ALH84001 still matters here, not because of the live debate, but because of what the contamination problem does to cases like it. When a meteorite might contain evidence of ancient Martian biology, and that same rock has passed through dozens of hands over decades, the presence of a polyester fiber or a trace of pen ink doesn't just embarrass the scientists involved. It permanently clouds the record. You can't uncontaminate a sample. Once the question of origin is muddied, it stays muddied. That's not a hypothetical risk. That's the situation these rocks are already in. Not every Martian meteorite is chasing the question of life. Some are answering quieter but equally important questions like what Mars's surface actually looked like and when. Researchers from the United States and the United Kingdom studied a specimen called the Lafayette meteorite and determined that minerals inside it were exposed to liquid water on Mars approximately 742 million years ago. Liquid water. On Mars. Nearly 750 million years ago. That single data point reshapes how scientists think about the planet's timeline. It suggests Mars held water far more recently than many models assumed, which keeps the possibility of past life in play for much longer periods of Martian history. This is exactly the kind of discovery that contamination threatens. If the organic chemistry inside a sample, like the Lafayette meteorite, gets compromised by ethyl alcohol from a cleaning protocol or diamond particles from a cutting tool, the timeline scientists work to reconstruct becomes impossible to trust. The data doesn't disappear. It just becomes permanently uncertain. The contamination findings in applied geochemistry aren't a story about careless individuals. They point to a structural problem in how rare scientific material gets handled over time. Martian meteorites pass through many hands: field researchers, transport teams, museum curators, laboratory technicians. Each handoff is a contamination risk. Pen ink from labeling, polyester from clothing, ethyl alcohol from cleaning protocols, diamond particles from cutting tools. None of these materials are exotic. All of them are exactly what you'd find in a normal scientific workspace. The problem is that normal isn't good enough when the sample you're analyzing might contain the only evidence of ancient Martian biology. With fewer than 400 specimens in existence and no sample return mission yet completed, there is no margin for error. Every gram of contamination introduced into these samples permanently narrows the questions we can still answer. The Lafayette meteorite's 742 million-year-old water signature and ALH84000 sun's decade-long wait before anyone looked closely. Both point to the same truth. These rocks reveal themselves slowly and only to scientists who handle them carefully. The system that protects these rocks wasn't built for material this rare, and the findings published in Applied Geochemistry are a warning that it needs to be. Every Martian meteorite in storage right now may be carrying questions we only get one chance to ask correctly. How we handle the next gram of Mars matters more than most people realize. If this kind of story is what you come here for, subscribe. There's more where this came from. And if you want to go deeper, the full article is on factstormhub.com.